To properly map the turbulent wake of a jet engine or the thermal dissipation across a microchip, we rely on rigorous mathematical definition. We possess the differential equations that perfectly describe these physical phenomena. But the reality is, for most complex geometries, those exact equations are practically unsolvable. To find a clean, analytical solution, modern computational physics requires a strategic compromise. We have to abandon the pursuit of a flawless analytical answer and instead seek approximate unknowns. The objective becomes extracting a manageable system of linear equations from the complex physical problem. When solved, these provide an approximation that is highly accurate and perfectly functional for engineering needs. Navigating these approximations requires a strict hierarchy of mathematical models. This entire field splits almost immediately into two distinct architectures, separated entirely by how they interpret physical space. On the left, we find discrete coordinate methods. This approach evaluates the differential equations at specific isolated points. On the right are distributed coordinate methods. Instead of looking at individual dots, this framework evaluates mathematical functions across continuous, unbroken spaces. Whether you choose to slice a physical problem into a set of discrete dots or treat it as a continuous distributed domain dictates every subsequent mathematical tool you can deploy. Let's start with the left side of the map to see how the discrete approach functions. The defining rule is strict localization. We evaluate the math where the grid intersects our model, allowing a fixed framework to ignore the space between points. The most heavily utilized tool on this branch is the finite difference method. At its core, it provides a straightforward technique for numerical differentiation. It estimates the slopes and changes strictly between those specific known points, but it comes with a severe mathematical caveat. To push a finite difference model to higher levels of accuracy, you are forced to aggressively increase the density and computational complexity of that underlying grid. That rigidity eventually creates a computational ceiling. The sheer cost of processing a microscopic grid pushes engineers to look for methods that can dynamically move through a domain. That need for motion brings us to the next subcategory on the discrete branch, stepwise integration. This is where we find engines like the Euler and robust Runge-Kutta methods. Rather than laying down a static grid, they calculate a tangent at a known point to predict the next coordinate. Because they rely entirely on knowing their exact starting position, they are highly optimized for initial value problems, where time zero is an absolute known. If you apply them to spatial boundary value problems, where conditions are set at the edges, you must use a brute force approach. You start at one edge and propagate blindly until you hit the other side. Since these methods are chained to step-by-step propagation, evaluating highly complex spatial boundaries becomes deeply inefficient. To handle complex geometries, we move to the right side of the map, distributed coordinate methods. Instead of isolated points, we define continuous functions across an unbroken spatial domain. The dominant toolset is weighted residual methods, dividing into boundary or interior measurements. Boundary residual methods, particularly the boundary element method, yield incredibly accurate results, but they demand exceptionally heavy mathematical computation to maintain stability. The far more versatile path lies inside the geometry itself, utilizing interior residual methods. This group includes techniques like collocation, the subdomain method, and heavily relies on the Galerkin method. By weighting and minimizing the residual errors over a continuous area, these interior techniques act as the exact mathematical engines required to map complex state approximations across continuous, unbroken space. But tracking residual errors is not the only way to evaluate a continuous boundary. There is a parallel branch known as stationary functional methods. This utilizes a completely distinct mathematical approach to represent the exact same differential equations. Instead of calculating an error term, this approach minimizes the total energy functions acting across the entire spatial domain. The prime example of this functional approach is Rayleigh's method. Developed by Lord Rayleigh, this technique provided early physicists a rigorous way to approximate natural vibration frequencies through energy conservation. Stationary functionals prove that we can arrive at an accurate, continuous model through energy principles just as effectively as we can through error weighting. When we pull back and examine the entire architectural build of this taxonomy, a crucial mathematical convergence occurs at the bottom of the map. Watch the flow of logic downward from the Galerkin method on residual side and Rayleigh's method on the functional side. Despite utilizing entirely separate sets of mathematical rules, one tracking errors, the other tracking energy, both of these distributed pathways yield the exact same approximate model. Both lineages successfully derive the finite element model. The finite element model stands as the ultimate convergence point of distributed approximation across the discipline. This dual derivability proves the absolute mathematical robustness of the method. Because it functions perfectly whether approached from a residual or a functional perspective, it guarantees an incredibly precise outcome. When we translate that theoretical convergence back into physical reality, we produce the complex physical simulations that build the modern world. The finite element model is the undisputed industry standard for computational physics. Its precision and its ability to adapt to nearly any geometric shape are direct outputs of its deep roots in continuous, distributed domain mathematics. Understanding this taxonomy clarifies exactly why engineers across aerospace, civil, and mechanical disciplines rely heavily on this converged model. By mapping the architecture of approximation, we realize that modern engineering simulation is driven by the elegant mathematical structures that safely bridge the unsolvable to the computable.